Hello everyone. So I'm Eremeev Iurii from the Laboratory of Semiconductor Devices and Integrated Circuits. We are working on the radiation detectors with internal charge multiplication for spectroscopic applications. So I'll start with a brief introduction to the radiation detection systems, their application and principle of operation. We'll concentrate on the semiconductor detector side, and I'll introduce low-gain avalanche diodes. Then we'll study the electronic noise of LGADs and the excess noise factor, and finish with the advantage of the LGAD structure and spectroscopy. So the application of radiation detection systems vary according to the type of radiation, energy, and system architecture. We can start with the medical imaging, go to material inspection with the baggage screening at the airports, food control at the enterprises, and material analysis at the laboratories. The most sophisticated systems are made for scientific experiments in astrophysics and particle physics. And most of the radiation detection systems are based on the detectors. So they're made of semiconductors, thick substrate with the thin epitaxial layer and the N and P doping layers to create the PN junction. When the reverse bias voltage is applied, the conduction band is depleted, and when photon arrives to the epitaxial layer, it creates electron-hole pairs, and the amount of charge is proportional to the photon energy. This is the basic principle of operation. So when we connect the semiconductor detector to the amplifier and the shaper, we create the radiation detection system. So when the charge is created in the structure due to the photon, the form of the peak has a delta function U, and then the current spike is amplified due to the amplifier. The shaper changes the form of the peak to make it measurable for the processing chain. And at the output, we have the peak which is proportional to the photon energy, and the time of arrival is used in timing applications. And so, however, for this system, we always have the noise, which is associated to all the electronic chain and the detector itself, including the current noise and the detector capacitance, because it multiplies the amplifier noise. And so from this point on, the question is how to increase the signal-to-noise ratio in this basic system. And so the idea is that we can use a detector with internal amplification. And this is low-gain avalanche diode. So here I showed the basic schematic of diode and low-gain avalanche diode. So the electric field distribution across the diode structure, we can see the high electric field across all the epitaxial layer. But in LGAD, we have a peak of the electric field under the output electrode, which is achieved by ion implantation of the P-gain layer under the electrode. So when the photon arrives, it creates electron-hole pairs, electrons travel to the gain layer, increase their kinetic energy, and start impact ionizing structural atoms. So we have more charge. The multiplication gain is defined as the ratio between the amount of charge coming out from the gain layer to the amount of injected charge. However, along with the signal in the structure, we increase the noise. And to study the noise, we have to measure the noise parallel spectral density at the output, which is actually was made. So this is the structure connected to the amplifier and spectrum analyzer. We don't use the radiation source in the system. We have the controlled temperature conditions. And so the charge is created thermally inside the epitaxial layer and gets multiplied. So when we increase the bias voltage in the system, the noise parallel spectral density increases by 4 orders of magnitude. And the main contribution to this noise is basically the current of the injected into the gain layer. So at the output, we have both contribution, the multiplied injected shot noise of the injected current and the excess noise factor. So the factor which is present due to the non-deterministic nature of the impact ionization process itself. And so to study the excess noise factor, we have to make some assumptions. The first assumption is that the injected current is the diode one, and the second assumption is that the DC gain can be calculated as the ratio between the LGAD and diode currents. In this case, we can draw this graph with the dependence of NPSD on the LGAD current. We can see the shot noise of the current measured at the same time with the noise parallel spectral density, then the multiplied shot noise, and the noise parallel spectral density we measure, which is higher than the multiplied shot noise due to the excess noise factor. And the additional consideration that the NPSD depends linearly on the LGAD current on logarithmic scale. In this case, we can just use the function to feed this data and equalize this function with the definition of the noise per spectral density with excess noise factor and derive excess noise factor. So this is the result of our measurements. The excess noise factor depends on the multiplication gain. The solid line is drawn using the parameters of the feed in the previous graph. And in literature, we have the dependence of the excess noise factor on the multiplication gain. So this is, for example, McIntyre model, which has one free parameter, the ratio of impact ionization coefficients for holes and electrons, and it cannot fit our data. So which is known in literature for the avalanche photodiodes with thin multiplying regions. So excess noise factor in McIntyre model is overestimated at low gains for APD with the thin multiplying region. And here we can see that the excess noise factor is low at low gains. So we can use this structure in spectroscopy. And what is the advantage? So here I show the setup we use to measure the spectra. So we connect the, in this case, diode to the amplifier and the multi-channel analyzer. And the test input is used to send the voltage pulses to the same processing chain. We can see the resolved peaks of the americium and quite big width of the pulsar of 2.4 kiloelectron volts. When we replace the diode structure with LGAT, having the same processing chain and the same bias voltage, we have this spectra. So the americium peaks are well resolved and the width of the pulsar decreased till 500 electron volts. And so the ratio of the width is about 4.4 for the gain of 6. So we have a large increase of energy resolution just due to the change of the structure. And this is not only the only message of this work, because to study the noise of the structure, we analyze the dark current parameters. So dark current is the DC component of thermal generation in the structure, and noise per spectral density as the AC component. And together we can find the optimal parameters to use this structure in spectroscopy without even radiation source. So thank you for your attention.